So, welcome to massive open online course on fluidization engineering. Today's lecture will be on minimum fluidization velocity and liquid solid system and gas liquid solid system. So, you know that as a recap we can say that minimum fluidization velocity for gas solid system can be calculated from this equation that this is the quadratic equation of Reynolds number for minimum fluidization condition. This is a function of course Archimedes number and or sometimes it is referred as Galileo number, and this minimum fluidization velocity depends on different factors like geometric variables, physical properties and also the thermodynamic conditions. Now, you know that for gas solid system this minimum fluidization system also is represented by a different way in terms of some parameters K1 and K2. So, this K1 and K2 actually is defined as the term that is obtained from the Argan equation, some parameters, and this form of this equation in terms of K1 and K2 that valid within the range of Reynolds number 0.0012 to 4000s. And using these values of K1 and K2, the minimum fluidization velocity can be obtained for different particle numbers. The particle number is greater than particle size is greater than 100 micrometer, then you can use this equation to calculate the minimum fluidization velocity. Whereas for if particle size is less than 100 micrometer, then you have to calculate the minimum fluidization velocity based on this equation. So, in this case this K1 and K2 are of course different for different ranges of particle size. And also there are various correlations that proposed by various investigators, like here one important correlations that is given by Bayes 1974 for gas solid operation, and then the minimum fluidization velocity can be obtained from this correlation. This correlation has been developed from the experimental data within the range of size less than 100 micrometer. Other different correlations that is given by Bayes and Geldart, even Argan in terms of this what is that Archimedes number along with the quadratic equation of this Reynolds number, and Leva et al. He has given these correlations, and even Goroshko et al. They have proposed this equation. There are several others different correlations that is given by different investigators for calculating the minimum fluidization velocity, and those correlations has been developed based on the experimental data. Now, what should be the minimum fluidization velocity for liquid solid system? As per Thonglim 1984, the correlation for liquid solid system they have developed based on the concept of whatever it is developed for gas solid system. It is also represented by this Archimedes number, and this is your minimum fluidization condition, what should be the Reynolds number, and this Reynolds number at the minimum fluidization condition will be obtained from this equation, whereas this Archimedes number will be depending or defined as this equation. So, Thonglim 1984 he has proposed this concept to calculate the liquid solid minimum fluidization velocity, and in this case another important recently developed correlations is given by Lee et al. In 2016 that how to calculate the minimum fluidization velocity for liquid solid system. Now, for this of course this concept also has been taken based on the concept whatever it is for gas solid system. This is the Argan equation part by which you can calculate the friction or pressure drop, and that will be balanced by the apparent weight of the bed. So, this from this by equivalency you can calculate the minimum fluidization velocity for liquid solid system. And here of course this this minimum porosity for this minimum fluidization condition, or you can say minimum voidage, that depends on the shape of the particle. For spherical particles, this epsilon mf, that is minimum voidage, minimum voidage will be within the range of 0.4 to 0.45. Otherwise, you can calculate the minimum voidage from this equation. This epsilon mf will be almost equals to 1 by 14 into phi s to the power 1 by 3. This phi s is nothing but the sphericity. So, other than spherical particle, you can calculate the minimum voidage from this equation. After getting this minimum voidage, you have to substitute this minimum voidage here in this equation, and and calculating the minimum velocity just by solving this equation. Now, what should be the minimum fluidization velocity in conical fluidized bed with solid fluid system? Now, see, there are different types of fluidized bed systems. Some conical fluidized bed is also one important. There are some advantages of this conical fluidized bed system. Here, you will see that of course, from this bottom, how conical part will be there at this location, and from this conical system you will see there are two diameters, that is dB, that is upper bed surface diameter, and this is the lower part, this conical portion, that is di at entrance, what should be the diameter here. So, this is the particle and particle here, and this is the fluidization regime here. This is the bed, fixed bed condition, and after fluidization, how this fluidization occurs and what should be the minimum fluidization for this solid fluid system in this conical fluidized bed. So, here you will see for this conical fluidized bed, of course, giving advantage because this circulation pattern will be changing here inside the bed. So that the mixing, maybe more intense mixing can be obtained by this conical fluidized bed. And also the solid circulation, this conical fluidized bed are more important due to the solid circulation inside the bed, and it will be very much beneficial for the physical operations like coating, like drying purpose, all those things. Now, what should be the then minimum fluidization velocity in this conical fluidized bed system? And here also this is a quadratic equation for the UMF here. So, that is also obtained by, or this is proposed by Zhou et al. 2009. So, he or they developed this equation by balancing this momentum, and then obtain this equation for minimum fluidization velocity. And in this case, this one important aspect that you have to know the minimum voidage for this solid fluid system here. This minimum voidage should be calculated based on this here 0.16 into Ug by epsilon mf and into Ug plus ULM f. Here in this case solid fluid means here you can say that in this case liquid also will be very important, gas liquid solid system. So, in this conical fluidized bed gas liquid solid system is more important here. So, for this gas liquid solid system, this alpha mf will be equals to this is based on the equation that is proposed, what should be the mixture velocity here for gas and liquid here. And this equation will be valid only for if the ratio of gas velocity to the mixture velocity of gas and liquid is less than equals to 0.93. And in this case conical fluidized bed system, of course, you have to calculate the diameter of the bed as an equivalent diameter at this minimum fluidization condition, and then minimum equivalent diameter can be calculated from this what should be the volume fraction of the solid inside the bed. Now, let us see example on gas solid and gas liquid system. So, let us see if a fluidized bed is operating with air at a minimum fluidized condition with a particle of cubes 0.02 meter on a side, the bulk density of the fluidized bed with air is 980 kg per meter cube. The density of the solid cube is given here, and the density of the air is given as 1.18 kg per meter cube. then viscosity of air is given like this. So, what should be the void fraction of the bed, how to calculate the effective diameter here, and also how to determine the sphericity of the cubes, and what should be the minimum fluidization velocity if you are using water at 20 degree centigrade and a bed diameter of 0.15 meter. So, under this condition, let us calculate this. Now, how to calculate this void fraction? This void fraction can be calculated. First of all, you have to calculate the total volume of the bed. Total volume means here total volume of the bed means volume of the fluid and the volume of the solid, and then weight of the bed will be equal to weight of fluid and then weight of solids. Now, what should be the weight of the bed will be equals to that density of the bed into the volume of the bed. Now, if and also what should be the volume of the what should be the mass of the fluid inside the bed, that will be volume and that is product of volume and density of the fluid. Similarly, for mass of the solids would be equal to density of the solid and into volume of the solids. But in this case, you will see there will be the solid mass will be much greater than the fluid mass. So, you can neglect this fluid mass relative to the solid mass. So, it should be then what should be the mass of the bed, you can directly calculate what should be the mass of the solid. So, if you know this mass of the bed by knowing this mass of the solid, then you can calculate what should be the void fraction here. So, void fraction will be equals to volume of bed minus volume of solid divided by volume of bed. That means, here what should be the amount of volume of space here except solids in the bed out of total bed volume, that will be your void fraction. So, this void fraction, then if you substitute here V bed minus here V solid means here from this equation V solid you can calculate rho bed by V bed divided by rho solids. So, here this for this V solid you can substitute here this portion, and then finally, you can get 1 minus here, you just divide it or separate it, then you will get this 1 minus rho bed by rho solids. Now, 1 minus this rho bed means here what will the bed density, effective density, it will be 980 kg per meter cube as per your problem, and then what is the rho solids, then it is coming here 0.35. Now, void fraction at minimum fluidization condition you can calculate from this equation given by Wen and Yu, that this from this equation. So, from this equation you can get this minimum void fraction will be equals to 0.445, whereas this without that means except
minimum void fraction it is coming 0.35. For minimum void fraction it will be higher than this actual fluidizing condition void fraction is 0.35. And effective diameter of the particle you can calculate from this here. First you have to calculate, if it is cubical, then you have to calculate volume of the cube, then it will be equivalent to the spherical particle, then it will be dp is equal to 0.025. Whereas the sphericity of the particle, then phi is equal to surface area of the sphere having the same volume and divided by this surface area of the particle AP. So, finally, you can get what should be the what should be the sphericity of the particle, it will be equal to 0.81. Now, for coarse particle, of course, if dp is greater than 100 micrometer, then the minimum fluidization velocity can be calculated from this equation, like here R E P M A P will be equals to 28.7 whole square plus 0.0494 into Archimedes number whole to the power half minus 28.7. So, this 28.7 this portion that is obtained from the parameter of this Argand equation. Now, this first you have to calculate the what should be the Archimedes number here. Archimedes number, if you substitute the different variables in this equation, then you will get the Archimedes number is this one 3,42,247.7. Then after that, if you substitute this Archimedes number here in this equation, you will get the minimum Reynolds number for this minimum fluidization condition, that will be equals to 104.45. Now, once you know this minimum Reynolds number, which is defined as rho f into UMF, UMF is the minimum fluidization velocity, then from this equation you can calculate what should be the minimum fluidization velocity. It will be exactly 3.15. Now, if we use this minimum porosity as 0.445 and the sphericity of 0.81, then you can get different you can get different fluidization velocity at this minimum condition based on this equation, where you have to calculate first K1 and K2. Here you have to use the equation which is a function of these parameters K1 and K2. Now, this REMF will be equal to this is a function of K2 and K1. Now, if you substitute this K1 and K2 value here, then we can get the Reynolds number at this minimum fluidization condition as 92.38. So, here from this we can calculate UMF, that means minimum fluidization velocity from this equation, that will be equal to 2.78 meter per second, whereas without using this minimum voidage of 0.445 and the sphericity of 0.81, and if you use this previous equation, then we are getting here 3.15. So, what will be the deviation from this if I use this K1 and K2 parameter? So, we have seen that it will be almost 11.7% error. So, almost it will be equal or near about to equal. So, we can accept this one also. Now, if the fluidization done with fluid as water instead of air, that means here liquid, solid and liquid system, then we can get this here according to that equation here. Instead of here rho z, it will be rho f, that means rho L, density of the liquid instead of density of gas. So, if we substitute the density of the liquid instead of density of air or gas here, then we can get the Archimedes number here this, whereas this if you substitute this Archimedes number in this equation, then you can get the Reynolds number at this minimum fluidization condition as this, and from this equation you can calculate what should be the then minimum fluidization velocity, and it is coming almost 0.076. What we observed here from this, if we use water instead of air, you will see that minimum fluidization velocity is drastically reduced here, of course, because of this viscosity. So, water has higher viscosity than gas, that is why this minimum fluidization velocity will reduced. And another example, I calculate the minimum fluidizing velocity for the fluidized bed operating with a sharp sand particles and with air under the following properties. Here fluidizing gas is ambient air, density is 1.2 kg per meter square meter cube, and viscosity is 0.00018 kg per meter second, whereas solid is sharp sand particles of diameter 75 micrometer, and phi s, that is sphericity, is given as 0.767 and density is 2600. Now, compare these values of minimum fluidization velocity calculated by different correlations. So, if we use here epsilon mf is equal to 0.45 as per the equation given by Wen and U, and the sphericity has 0.67, and then we can calculate what should be the parameter K1 and what should be the parameter K2. So, from these parameters K1 and K2, we can calculate what should be the Reynolds number at this minimum fluidization condition. So, if we once know this Reynolds number at this minimum fluidization condition, we can obtain the minimum fluidization velocity from this Reynolds number as this one. So, here very interesting that we can calculate the minimum fluidization velocity, which is depending on different variables like porosity, like minimum void fraction, like density of the fluid, like viscosity of the fluid, and particle size. Here in this case the particle size is very low, that is why your minimum fluidization velocity is coming almost near about 0, not exactly 0, but it will be very low. Now, as per correlation of Bayes, if we substitute all the variables here in this correlation, and then we can get the minimum velocity as 0.00385, whereas in previous case we have calculated the minimum fluidization velocity at 0.00395. Here it is coming as 0.0019, sorry 0.395, and in this case it is coming 0.0385. So, 385, 395, it is nothing, there is only hardly 2.6% error. Whereas, if we calculate the minimum fluidization velocity by different correlations, like correlations of Leba, you can get the minimum fluidization velocity 0.699, whereas Goroshko et al. Based on their correlation, you can get the minimum fluidization velocity like this. So, in this table it is given the minimum fluidization velocity obtained by different correlations here, and from these correlations we see that we can get mean value of 0.650, and what should be the deviation from the different correlations we can calculate, and then it is seen that very deviation from the mean is not that much of significant. So, any correlation you can use for the design aspect of this minimum fluidization calculation. Now, minimum fluidization in gas, liquid, solid system. So, up to this we have calculated the gas solid and liquid solid. So, we can easily calculate what will be the minimum fluidization velocity, but in case of gas, liquid, solid system, their interaction of the solid particles with not only single gas or single liquid, here both the gas and liquid simultaneously will be there. So, in this case the frictional pressure drop in case of gas, whatever it is, we have not actually considered the hydrostatic pressure there, but in this case of course one should consider the hydrostatic pressure of course. So, in this case gas, liquid, solid system, the measured pressure drop here it will be equal to frictional pressure drop along with the hydrostatic pressure drop. So, this hydrostatic pressure drop can be calculated of rho ZH. Here rho will be the mixer density. For how to calculate this mixer density? Mixer density will be equals to rho L epsilon L plus rho Z epsilon G plus rho S epsilon S. Now, what is epsilon L? Epsilon L is nothing but the volume fraction of the liquid in the gas, liquid, solid 3-phase systems, and epsilon G is the gas volume fraction in this total phase of gas, liquid, solid. And what should be the solid fraction? That will be denoted by epsilon S, and this is the volume fraction for solid. So, this mixer volume depends on this volume fraction of gas, liquid, solid. So, this will be your volume of liquid, this rho Z into epsilon G, it will be volume of gas, density of the effective density of the gas, and rho S epsilon S, it will be the effective density of the solid. So, total density of this liquid, gas and solid will be equals to mixer density of the 3-phase system here. So, if you know the mixer density of this fluidization system, then of course, you can calculate what should be the hydrostatic pressure there. So, once you know this hydrostatic pressure, and what should be the frictional pressure drop. So, frictional pressure drop will be equals to frictional pressure drop will be equals to measured pressure drop minus delta P H, that means here hydrostatic pressure drop. Now, if void is of the bed, that means only fluid part. If you know, then what should be the density of the fluid. That means here fluid means solid and gas mixture, not will not be considered as solid here. So, only just considering the gas and liquid here. So, only these two parts, suppose in the fluidized bed, this is the part is here, this is gas and liquid, and this is solid. So, this is solid and this is gas plus liquid, gas plus liquid. So, if we consider only this gas and liquid, what should be the void of this void fraction of this gas and liquid? That means, what should be the volume that is occupied by this gas and liquid. So, if we represent that much volume fraction of this gas and liquid as epsilon, then we can say here rho f into epsilon, that this rho f is nothing but mixture density of fluid only. That means, the density composite density of the gas and liquid here. So, this density into this void fraction of gas liquid, this would be equals to rho g epsilon g plus rho L epsilon L, g for gas, L for liquid here. So, what should be the density of the liquid here? It will be rho g epsilon g plus rho L epsilon by epsilon here. This epsilon is the total volume fraction of the gas and liquid portion only, and this F stands for here fluid mixture, and the fractional hold ups of gas and liquid in gas liquid mixture then can be represented respectively by, then here if we take this part, that means here rho g epsilon g by epsilon, and then it will be equals to what will be the fraction of this part, and then what should be this part epsilon g, this volume fraction of the gas to the total volume of gas and liquid, then it will be your fractional hold up of this gas here. And for liquid, of course, it will be equal to epsilon L by epsilon. If you add this alpha g and alpha L, alpha g and alpha L, alpha g plus alpha L, that will be equals to 1.0. So, alpha L should be equal to 1 minus alpha g. So, therefore, we can say that rho f will be equals to rho g alpha g plus rho L into 1 minus alpha g. Now, for homogeneous mixture of gas and liquid, if we consider there will be a homogeneous mixture of gas and liquid in gas liquid solid system, then the superficial fluid velocity of homogeneous gas liquid mixture can be calculated as here USH, that will be the mixture velocity of liquid and gas. Here S stands for superficial, H stands for homogeneous, and USL, that means superficial liquid velocity, in this case it will be calculated as what should be the volumetric flow rate of liquid by cross sectional area of the bed. This will be your superficial liquid velocity, whereas superficial gas velocity is defined as what should be the volumetric flow rate of gas. If you divide it by its cross sectional area of the bed, then you can get the superficial gas velocity by this equation. Now, the homogeneous fluid density of the gas liquid mixture, then what should be the homogeneous density here? Of course, you can say as per this rho f, this will be nothing but rho f, then it will be rho g epsilon g plus rho L epsilon L divided by total volume fraction of gas and liquid mixture in the bed. So, if we simplify this equation by neglecting this gas mass relative to this liquid mass, then you can get this homogeneous density of the fluid inside the bed as rho L epsilon L by epsilon, that will be equal to 1 minus alpha g into rho L. Now, the frictional pressure drop for the homogeneous mixture as per Wallis 1969, that it can be expressed as here. In this case, of course, this frictional pressure drop will be a function of homogeneous mixture velocity and the density of the mixture, as well as what should be the volume fraction of the liquid and gas, that means fluid, total fluid inside the bed, and also the what should be the projectional area of the solid particles inside the bed. So, if we know the frictional pressure drop from this Wallace equation here, of course, we can equalize this homogeneous frictional pressure drop of this equation with the total mass of the bed, then from which you can calculate the minimum fluidization velocity for the gas liquid solid system. Now, see this Wallace equation, there is one factor that is called friction factor. A friction factor, this friction factor of course will be the in between the particle and of course the particle surface or solid surface to the gas and liquid. So, it will be represented by this FS. FS means fluid and solid surface. Now, this solid surface including the wall also. So, here the friction is with the solid and the homogeneous mixture of the gas and liquid. The buoyant weight of the solid particle is supported by this upward homogeneous fluid drag on the particles. This is your fluid drag by what is calculated with the frictional pressure drop. And then we can say this buoyant weight will be balanced by this frictional pressure drop as this G into 1 minus epsilon into rho s minus rho s at this gas liquid solid fluidization condition. Now, if we equate these two equations, then of course, we will get the minimum fluidization velocity. Before going to that, you have to of course calculate the frictional projected area of the particles, because this is required for calculating the frictional pressure drop, or you can say that fluid drag by this Wallace equation. So, for this what should be the AP, that means here projectional area of the particle, surface area per unit volume, you can say also this will be calculated by 3 by 2 into phi s into dp. Phi s is the sphericity. Now, when the liquid velocity increases and gas velocity remains constant, the ratio of epsilon L by epsilon increases, and so density will increase. Thus, in contrast with the two phase fluidized bed, this frictional pressure drop decreases, and also the what should be the drag coefficient, or you can say friction factor FFS, that will of course will be depending on this porosity or void fraction of the gas and liquid mixture here. And this is of course is a function of void fraction and the friction factor if we consider only solid particles there, not gas and liquid. So, in that case for single fluid solid system, you n this n is the coefficient, n is equal to 4.7, whereas for gas liquid solid system n will be is a function of superficial gas velocity, and that can be calculated from this equation. N will be equal to 5.7 minus 8 into USG. So, once we know these equation, you have to substitute in Wallace equation, then you can get the fluid drag by this Wallace equation. Now, what should be the individual solid phase friction factor, which is required here in this equation of equation 16. So, you can calculate this individual solid phase friction factor Fs which is developed by Rho 1961 for 3 phase flow system, as this Fs will be equals to 24 by Re alpha into 1 plus 0.15 into Reynolds number to the power 0.687. Here this equation valid for if Re alpha, that means here Reynolds number based on terminal velocity if it is less than 1000, whereas it will be only 0.44 if it is more than 1000 and less than 10 to the power 5. Then Fs you can calculate for the single solid phase friction, and Re alpha, that means the Reynolds number based on the terminal velocity will be equals to Ut rho h dp by mu h. Here mu h is the viscosity of homogeneous mixture of gas and liquid, and Ut is the terminal velocity of the solid, and rho h is the mixture density of gas and liquid only, and dp is the particle diameter, and from which you can calculate the Re alpha. and if you substitute this rho L as 1 minus alpha g into rho L, then you can get here this Reynolds number, which is a function of again this alpha g. Alpha g is the gas void fraction, that is fractional hold up of gas inside the bed. So, this Reynolds number of course will be changing with respect to the how much gas is obtained, how much gas is actually occupying in the bed. So, fractional gas hold up of the system, that will enhance the that will affect the Reynolds number, and which directly will be related to this what is the friction factor here. Now, what should be the terminal velocity? Of course, this terminal velocity will be that already we have shown earlier also, that 4/3 phi s dp g by f s. This f s, of course, this is a friction factor, which is again is a function of Reynolds number, is a function of again terminal velocity. So, this is the nonlinear equation for terminal velocity here. By trial and error method, you have to find out the terminal velocity from this equation. Now, for any gas, the liquid velocity at which the bed is operated, the gas hold up in the 3-phase bed can be predicted as per Marquardt 1963. He has developed this correlation for calculating the gas hold up in the gas liquid solid 3-phase system. So, this is a function of superficial liquid velocity, particle diameter, even solid density, even superficial gas velocity, density of the gas and liquid, viscosity of the liquid, and also the bed diameter. So, all those parameters here, if you substitute these parameters or variables here in this equation, then you will get the fractional gas hold up in this 3-phase system. Otherwise, you can calculate this gas hold up by experimentally. So, here the gas hold up alpha g can be experimentally obtained by the phase isolation techniques. What is that phase isolation techniques? At the running condition, you have to observe how much gas liquid solid level inside the bed is up to that, and suddenly if you stop this operation, you will see the gas inside the bed will disengaging and it will be dissolved at the top, and after a certain time, after degassing all the gas here, there will be a clear liquid solid mixture height inside the bed. Then if you know the clear liquid height here as L c and the mixture height as L m, then you can obtain the gas hold up experimentally by this equation L m minus L c by L m. What is that? See, alpha g is nothing but the gas volume upon total mixture volume. So, this you can represent it as gas volume as mixture volume minus clear liquid volume here. Now, this mixture volume will be calculated as A into L m. L m is the minimum fluidizing height there, and A is the cross sectional area. So, this is the volume of bed at the minimum fluidization condition, and this ALC, this is the volume after degassing all the gases in the gas liquid solid fluidized bed. And if you subtract this, then you will get the total gas volume here, whatever occupied in the gas liquid solid fluidized bed. And this ALM is the what will be the minimum fluidization condition, what will be the total volume of gas liquid solid mixture. So, from which you can calculate what should be the gas hold up by this isolation technique. Otherwise, you can directly without doing experiment, you can calculate this alpha g from this Marquardt equation. Now, see what is that if you use this Marquardt equation here alpha g for the minimum fluidization condition, then it will be alpha g m minimum fluidization condition, then here it will be USL m at the minimum fluidization condition, here again MF minimum fluidization condition, here again it will be considered as minimum fluidization condition. So, to calculate the minimum fluidization condition again with a function of again minimum fluidization liquid and solid gas velocity, then it will be a nonlinear equation. So, now from equation 13 and 14, if you consider or if you take into account the expressions for homogeneous mixture fluid velocity and homogeneous fluid density, and the AP from the equation 15 and the friction factor from equation 16 for a certain gas velocity, then following equation can be obtained for the frictional pressure drop and the porosity as like this. So, here delta P F H will be equals to this here, and this is nothing but what will be the apparent weight of the bed here in under this fluidization condition. So, after rearranging this equation 22, you can get epsilon, that means what will be the void fraction that is occupied by the mixture of gas and liquid only, not solid. Okay, that will be depending on the particle diameter and also the volume fraction of the gas and also density of the liquid, gas and liquid velocity inside the bed. So, this will be your void fraction, that is of gas and liquid here for gas, liquid, solid system. Now, equation 22 together with the equation 15 to 20, one can obtain the minimum superficial fluidization velocity of the liquid here. So, this will be as for liquid here. So, this will be obtained after rearrangement, and again it is a function of USG here. So, see USMA, that means minimum fluidization condition. What will be the minimum liquid velocity by which you can get the minimum fluidization condition for the gas, liquid, solid system? Now, this is again is a function of, see here, epsilon MF, and this epsilon MF is a function of this is again the liquid velocity and gas velocity. So, that liquid velocity will be considered here, see, liquid velocity will be considered as a minimum condition. And then here alpha GMF at minimum fluidization condition, what should be the fractional gas hold-up, that can be obtained from this equation that is given by Zhang et al. 1998. This is again a function of gas velocity and the liquid velocity. Now, this liquid velocity you have to consider at minimum fluidization condition. Now, if you substitute here in this equation for alpha G in equation 24, then you will see the minimum fluidization velocity for liquid is a again function of minimum fluidization velocity for liquid. So, this is totally a nonlinear equation. You have to solve this nonlinear equation or optimize this nonlinear equation for liquid velocity by different optimization techniques, or by trial and error method you can calculate what should be the minimum velocity for liquid in the liquids, gas, liquid, solid system. Then for this minimum voidage you have to obtain here again by this O n and U model, what should be the minimum minimum voidage at this minimum fluidization condition, that is a function of sphericity of the solid particle. Now, different investigators they have developed different correlation from their different experimental data and obtain the minimum fluidization condition for liquid solid system, gas, liquid, solid system, even gas solid system also. We have already shown different correlations for minimum fluidization condition for gas and solid system, even liquid and solid system. In this case, the liquid, gas and solid system, the minimum condition can be obtained from those gas and solid and liquid and solid system also. If you know the two phase minimum fluidization condition, you can obtain the three phase fluidization condition by this equation of Begovi's by this equation here. So, this is here the minimum fluidization velocity for gas, liquid, solid system, and this is your minimum fluidization condition for liquid and solid system. So, this is a function of this gas velocity, viscosity of the liquid, particle diameter, density of the solid and density of the liquid. And this minimum fluidization velocity for liquid and solid system, it is a function of again Archimedes number, which is a function of fluid density, particle density, even viscosity of the liquid and the diameter of the particle. So, once you know this Archimedes number, you can obtain this minimum velocity in case of liquid and solid system, and if you know the minimum velocity in case of liquid and solid system, you can substitute here, and also with the other parameters, other variables, you can get the minimum velocity of gas liquid solid fluidization from this equation 27. Now, Zhang et al. 1988 they have developed the minimum fluidization velocity for 3-phase fluidization system based on the concept of gas solid system. Here it is called gas perturbed liquid model. So, again they have obtained the minimum Reynolds number based on the equation here. This Archimedes number is defined in different way here. So, instead of gas density they have considered here liquid density. So, from this equation you can calculate the what should be the Reynolds number at this minimum condition, and this is a function of again the minimum voidage of gas which is a function of gas velocity and the minimum liquid velocity in this 3-phase fluidization system. So, this model actually applied to this 3-phase fluidization involving Newtonian liquids, which equates the liquid buoyant weight of the solids per unit bed volume to the frictional pressure gradient, which is given by the Argan packed equation, and also it is applied to the liquid solids part of the incipiently fluidized bed. So, this Zhang et al. Model can also be used to calculate the minimum fluidization velocity in gas liquid solid system. Lin et al. Very recently they have developed another one correlations to calculate the minimum fluidization velocity in gas liquid solid system, which is given by this R E dash G M F. It will be equals to 33.7 square plus 0.0408 into Archimedes number. This Archimedes number based on the density of the liquid and gas in composite way. So, here this the definition of this Archimedes number, here we will see that only if we consider the gas and solid system, the density of the gas here it will be considered, whereas in liquid and solid system if we use the same concept, then Lee et al. As per Lee et al. It is defined as rho L instead of rho Z. So, here this Archimedes number of L G, that means gas liquid and gas system, here rho Z into rho S minus rho L into G into dP cube by mu G square, but this viscosity of gas will be considered here instead of liquid viscosity. For gas solid system, it is seen that this REMF is a function of again Archimedes number, but only it is a it is based on gas density, but other terms here see 33.7, here also 33.7, all these are same, all the coefficient also are same. So, only here instead of rho L it will be instead of rho Z, here it will be coming rho L. So, this should be noted. Now, for low liquid velocity, Zhang et al. Also given another equation to calculate the minimum fluidization velocity. Now, turning now to that closely related situation where there is a small liquid flow far less than that required to fluidize the solids, revert to previous equation, inserting just epsilon mf here, then you can get this equation for Reynolds number. Now, this applicable for superficial velocity only if it is less than equals to 0.98, and it is not it is valid only 0.98 to 1, not it is the earlier for gas solid system earlier model they have shown that it will be applicable only up to 0.93, but it is here this applicable up to 0.98 to 1. So, here this alpha mf, this is that means here minimum voidage for gas, it is again a function of this angle at a different angle orientation of the fluidized bed, how this gas hold up will be changing, that has been incorporated by this equation here. So, this equation will give you at any angle of the inclination of the bed, you can calculate directly the minimum gas volume fraction here. So, So, if you know the minimum gas volume fraction, then you can get the minimum fluidization velocity from this equation. Note that here if x is equal to 1, that means ratio of gas velocity to the mixture of gas and liquid equals to 1. That means if USL equals to 0, that means there is no flow of liquid. This above equation yields that epsilon mf into alpha mf will be equals to 0.406, which implies that since alpha mf equals to 1 for this condition, this alpha mf epsilon mf is equal to 1, a reasonable value for the minimum fluidization voidage of impermeable spheres. So, this is very important to be noted down. Lee et al. 2016, they have developed another type of correlation like here. This is actually developed based on the dimensional analysis incorporating all the variables in their experiments. Now, they have taken it and they have they have done dimensional analysis and obtained these groups as Archimedes number, Froude number, even ratio of hydraulic diameter to the particle diameter, even what should be the height of the fluidized bed and also what should be the diameter of the fluidized bed and also what should be the ratio of surface tension of the liquid to the surface tension of the water. So, from those they got this dimensionless group and done the regression analysis with this dimensionless groups with the experimental data, and they got the equation for its coefficient 0.103 and 0.7933 and other coefficient like this. Here in this equation it is given, and this equation, from this equation you can calculate what will be the minimum fluidization velocity, but it is applicable only if ReLMF will be equally less than 1, whereas if ReLMF is greater than 1 but less than 120, they have developed another correlation based on the same dimensionless groups, and they got different coefficients like this by multiple regression analysis. So, this equation also can be used to calculate the minimum fluidization velocity. In this case, you will see this SS, S is the static bed height. What is the static bed height? ds is the inner diameter of the fluidized bed or hydraulic diameter. You can consider here if it is two-dimensional bed, and sigma is the surface tension, and Froude number is denoted by Fr, which is defined as Ug square by GdP. Now, minimum fluidization velocity in conical fluidized bed with three-phase system, they have done some experiments with the conical flask also with this three-phase system, and they got this minimum fluidization velocity, which is expressed by the minimum Reynolds number, and again they have considered some parameters here and K1 and K2, but this K1 and K2 is a function of the diameter in the inlet and the surface of the bed. So, K1 is defined as di by dB, and K2 is the nothing but what is the dB by di and dB by di, and also alpha mf, this minimum gas void fraction, is a function of again this gas velocity and liquid velocity. And this is applicable only for if the ratio of gas velocity to the mixture of gas and liquid velocity is less than 0.93. Now, then this equation can be applied if you know this K1 and K2 for this conical type of fluidized bed, and if you know the ratio of this gas and liquid velocity inside the bed, you can easily calculate the minimum fluidization velocity for the conical fluidized bed in three-phase system. Thank you for this today's lecture. Next lecture will be given on that other part of this fluidization engineering. Thank you.